Welcome back. So in the last few lectures, we showed how to solve matrix systems of differential equations, x dot equals ax, where x is a vector of states and A is a matrix. So this is a coupled system of first-order differential equations. And what we showed was that by finding the eigenvalues and eigenvectors of this matrix A, we can transform the system into a diagonal form where it's easier to solve. So now I'm going to give you a few examples. And in this lecture, I'm going to start with a specific example A matrix. Maybe I'll use orange. So I'll use one of the A matrices that we've looked at before, which is 3, -1, -1, 3, 3, -1, -1, 3. And we've already computed the eigenvectors and eigenvalues of this A matrix in one of the last lectures. So this was one of the examples of how to compute eigenvalues and eigenvectors. So if I remember, what we have is the matrix of eigenvectors was, I think it was like 1, 1, 1, -1. And the matrix of eigenvalues, this diagonal matrix D, is, I think it was a diagonal of 2, 0, 0, 4. So we had two eigenvalues, 2 and 4, and these two corresponding eigenvectors. So the eigenvector corresponding to eigenvalue 2 is 1, 1, and the eigenvector corresponding to eigenvalue 4 is 1, -1. Okay, good. And so now what we're going to do is we're actually going to go through and compute the solution of this differential equation with this A matrix using that formula we had before. And I believe that formula was something like, x of t equals e to the A matrix. I'm going to maybe drop the under bars for matrix. We know this is a matrix. E to the matrix AT times initial condition x naught. And we wrote this e to the AT as, I believe we wrote it as t times e to the diagonal matrix times time times t inverse times x naught. And so I know what big T is, my matrix of eigenvalues. I know what diagonal matrix D is. And so now all I have to do is compute this T inverse, and we're good, we're golden. We can write down this full solution. So I'm going to do that, and then I'm going to draw the phase portrait. I'm going to actually draw in the kind of x1, x2 plane, what do all of the possible trajectories of this system look like. Good, so I'm going to compute T inverse really quickly. This is pretty easy. This is just kind of like a review of matrix algebra, really. So this is not super duper interesting. If you already know how to compute T inverse, just fast forward past when I compute T inverse. So to compute T inverse, the technique, I still use the same technique that we were all taught in kind of high school, where you go through a bunch of row operations. So what you do is you start with the matrix you want to invert on the left, 1, 1, 1, -1. This is just the T matrix. And then next to it, maybe I'll actually use colors here. Next to it, you draw the identity matrix 1, 0, 0, 1. And what you do is you go through the motions of row operations, like subtract this row from this row, or divide this one by -1, things like that, until the green matrix on the left looks like the identity. And you apply all of those operations to the blue matrix on the right. And in the process of making this left matrix the identity, you will turn this matrix into the inverse of T. Kind of cool. Maybe I'll have a whole lecture on why that's true. You can just take that for granted right now that that is true. And so I'm just going to go through pretty quickly. So the first thing I'm going to do is subtract this row from this. So that's, I'm sorry, what am I going to do? I'm going to subtract the first row from the second one to get 1, 1, 0, -2. So I subtracted this row from this row to try to turn this guy into a 0. And I do the same thing with my blue over here. So the bottom row is now -1, 1. Good. Now what I do is I'm going to divide this second row by -2, because I want this to be diagonal. I want it to be 1, 1, and 0s off the diagonal. So I'm going to divide this by -2, this row by -2. And so again, nothing changes on the first row. It's still 1, 1. But now this becomes 0, 1, because I divided by -2. Similarly, nothing changes up here, but now this row gets divided by -2. So now I have 1/2 and -1/2, or 0.5 if you like. And then finally, is this the last step? The last step is I'm going to now subtract this, this row from the first row to kill this, this guy here. Okay, so maybe I'll just write it down here because I don't want to mess up my board. So the last step is now subtracting the bottom row from the top row, so this actually turns into the identity. And now you can see that if I subtract the bottom row of blue from the top row, I get 1/2, minus a -1/2 is another 1/2, 1/2 minus 1/2. So 0.5, 0.5, 0.5 minus 0.5 is the inverse of 1, 1, 1 minus 1. Okay, that's how we do the inverse. That took a couple of minutes, not a big deal. I really hope I didn't mess that up, but I think this is okay. And I'll just write that out here, that T inverse equals 0.5, 0.5, 0.5 minus 0.5. And so now I can actually write out the full honest-to-goodness solution of my differential equation. Maybe I'll go back to pink here, by taking this T matrix times e to the diagonal d times T inverse. Okay, so I think I'm actually just going to write this out. So x of t equals my matrix T, which is 1, 1, 1 minus 1, times my matrix e to the diagonal d times t. And we know that this exponential of this diagonal matrix times time is just another diagonal matrix with those exponentials. So it's another diagonal matrix with e to the 2t and e to the 4t on the diagonals, 0, 0. Okay, good. And now I have T inverse times T inverse equals, 0.5, 0.5, 0.5 minus 0.5. All of that times x naught. Okay, this is what x of t equals. And I'm just going to multiply this out. This is actually pretty easy to solve, so I'm just going to do it. This equals 1, 1, 1 minus 1 times, okay, now I'm going to multiply these two matrices. And so I take this guy, knock it over on its side, times this row. So I get 0.5 e to the 2t and then on the bottom 0.5 e to the 4t. That's my left column. My right column, I take this second column, knock it on its side, and multiply each of these rows. And again, I get 0.5 e to the 2t, and I get minus 0.5 e to the 4t. Pretty easy, all of that times x naught. And finally, I'm going to multiply this matrix by this matrix. Let's hope I don't mess anything up. Multiply, again, same basic formula, and I'm going to get, what am I going to get here? Yeah, I'm going to get 0.5 e to the 2t plus 0.5 e to the 4t. Down here, I'm going to get 0.5 e to the 2t minus 0.5 e to the 4t. And then for the right column, I'm going to have 0.5 e to the 2t minus 0.5 e to the 4t. And then the bottom right is going to be 0.5 e to the 2t. Negative is plus 0.5 e to the 4t. All of that times, and now I'll actually write this out as a vector, x1 initial condition and x2 initial condition. So my initial condition vector has two components because this is a system of x1 and x2. And so we can write that x1 at a future time and x2 at a future time are equal to this system of equations. Now, I guess if I really wanted to write this out completely, fully, what I would do is I'd actually multiply this guy over, and I'd get x1 of t equals, all of this stuff times x1 naught plus all of this stuff times x2 naught. And x2 of t is all of this stuff times x1 naught plus all of this stuff times x2 naught. That would be the full-blown solution in time. And you could plot that in MATLAB. You could play around with this, and that would be pretty easy. pretty easy to actually work out. Good. Yeah, that wasn't very bad, actually. That was pretty easy. Maybe I'll just write this in slightly easier notation. I'll just say this is 1/2 of, e to the 2t plus e to the 4t, e to the 2t minus e to the 4t, e to the 2t minus e to the 4t, e to the 2t plus e to the 4t. All of that times x1 naught and x2 naught. Okay, so this is how you actually solve this differential equation. This is the actual solution. If you wanted, x1 of t, multiply this out, and that's the first row. The second row equation, x2 of t is equal to the second row, so multiply that out, and you get just a function of time. Okay, but this is actually not how I plot things. So what I want to convince you of is that actually these eigenvalues and eigenvectors are actually even more useful. Like when I draw the solution of differential equations, and I'm a very geometric pictorial person. I understand things best when I draw pictures, when I think of like the cartoon of how these dynamics evolve. I actually don't work in this pink or blue space here. I don't actually, if I want to actually write down the solution or plot it in MATLAB, I might work here. But if I want to draw a picture, I work up here in eigenvector coordinates. And so that's what I'm going to show you last, is how to actually plot the solution of this differential equation in these phase coordinates with the eigenvalues and eigenvectors. And so I hope I saved enough space over here to do that. And there used to be this really cool software package called P-Plane. I'll just write this up. It was called P-Plane, and you might still be able to download this and get it running. I think it used to run in like Java and MATLAB, and you could enter an ordinary differential equation and plot the phase portraits that I'm about to plot for you. There are other ways of doing that, but P-Plane made it really, really easy. If you know of another thing like this, another software package in Python or MATLAB that lets you plot these phase portraits, put it in the comments and I'll put it in the description, because this is really nice to be able to do this. Okay, and I need some colors here. So what I'm going to do, my eigenvectors I'm still going to draw in orange, and my basic axes I guess I'm going to draw in yellow here. Let's see, am I off the edge? Probably off the edge. Okay, that's this is the x1 and x2 directions, okay, because this vector x here is x1, x2 stacked into a vector. Okay, that's what that means. And the way I actually plot these things is, remember what our eigenvectors meant. Our eigenvectors were directions in which the dynamics were decoupled and diagonal, meaning that in this eigenvector direction, the dynamics are, kind of only depend on that variable in that direction. And so the dynamics in this direction are e to the 2t. That's like, or like a z dot equals 2z. That was what the dynamical system was. And in this other eigenvector coordinate, the dynamics are also decoupled, and they have the dynamics, z dot equals 4z, a different dynamics. So I'm going to draw these, and I think what I'm going to draw is this eigenvector in the 1, 1 direction. I'm just going to draw that whole plane, that whole kind of direction of xc1. So this is, sometimes we call this these eigenvectors xc. So this is the xc1 direction, and then the xc2 direction was in the 1, minus 1 direction. So this is the xc2 direction, and I'm drawing the whole kind of xc1 and xc2 planes. And again, what we learned about eigenvectors and eigenvalues was that for this differential equation, and I wrote this down before, something like if you had x equals tz, then z dot were equal to this diagonal matrix z. And literally z1 and z2 are the components in these eigenvector directions. z1 is how much of my state is in this c1 direction. That's literally what this means. So z1 is in this direction, and z2 is in this direction. And what that means is that in this new coordinate system, c1, c2, my dynamics become completely decoupled. So the dynamics in c1 have nothing to do with where I am in the c2 direction, and the dynamics in c2 have nothing to do with where I am in the c1 direction. And that's really, really useful. So any component of my vector in this direction is going to have very simple dynamics, which is basically, z1 dot equals 2 times z1. In this direction, these are the dynamics. And in this direction, z2 dot equals 4 times z2. Now, these are both unstable, okay, because my diagonal eigenvalues are positive. I get e to the positive 2t and e to the positive 4t dynamics, which means both of those blow up to infinity as t goes to infinity. As t gets big, e to the 2t gets very, very large. And so in both of these directions, if I start with an initial condition, and maybe I'll do kind of, if I start with an initial condition here, it's going to kind of follow that C1 subspace. It's never going to kind of move off of this line because it's, again, diagonal and decoupled. So it's only going to move in that line. And it's going to move with dynamics e to the 2t. It's going to move away from the origin faster and faster and faster. And the distance is going to be e to the 2t. Same thing with this direction. So I'm going to draw a little unstable arrow here. Maybe I'll draw this in blue. I have this little unstable arrow here and here, which says if I start in this direction, I will flee from the origin at a rate e to the 2t in this c1 direction. And similarly, if I start with an initial condition on the c2 direction, I will also have an unstable growth of e to the 4t. And e to the 4t grows faster than e to the 2t, so I'm going to draw two little arrows here just to give myself a little reminder that things actually grow faster in the c2 direction than the c1 direction. And so now we're ready to draw the phase portrait, kind of all of the trajectories from any initial condition. So again, if I started exactly on this c1 vector, that would correspond to a system state that had a non-zero z1 and a 0 z2. If I have nothing in the c2 direction, that means z2 is 0. And so if z2 starts as 0, it'll always be 0, and I'll stay on this subspace. So any time I start on c1, I stay on c1. Anytime I start on c2, I stay on c2. Again, that means I started with a z2 equals something and a z1 0. Okay, that's this line. But now let's say I start with some other initial condition. I start with some point, here, or some other point. We know that this point is going to flee from the origin. It's going to grow unstable because all of the dynamics are moving me away in both directions. They're moving me away. But this one is moving me away faster. And it's moving me away kind of almost twice as fast, right? Like e to the 4t is like this thing squared. And so that means that what I'm going to do is I'm going to be following these parabolas in this direction if I started for these different initial conditions. And if I start from an initial condition over here, I'm going to get the same kind of parabolas, but this way. Okay, and these are all moving out towards infinity. Okay, we know that this system is unstable. So any initial condition except from the initial condition at the origin, all of those initial conditions are going to blow up. Similarly over here, now if I have a positive z2, these were kind of the negative z2 direction, these are the positive z2 directions. These are also going to have these kind of parabolic trajectories where they are going to flee from the origin, and they are going to flee faster in this c2 direction, because that is a bigger unstable growth rate. So these are all moving like this. And similarly, I can draw this picture here. I hope you can tell I really like drawing these pictures. I've been drawing these for a long time. And so this is the phase portrait. This is kind of the pictorial geometric picture of what any trajectory in the system is going to do. From any point, they're going to flee from the origin with an exponential growth rate. And because the C2 or the Z2 dynamics are faster than the C1 or the Z1 dynamics, we know that we're going to get these kind of parabolic shapes. So it's going to flee in a particular pattern away from the origin. The only points that aren't going to is if I started exactly at the origin where x equals 0, then x dot equals 0, and I stay there. That's called a fixed point. So there is a fixed point at x equals 0. And that's the only point that won't move in this system. Every other point is going to move away. Good. So really, really interesting. Again, I just used my intuition from eigenvalues and eigenvectors to draw this picture. I didn't use this blue formula. I didn't use any of this pink formula. I used my intuition from eigenvalues and eigenvectors to draw this picture entirely. I knew that my dynamics were unstable. I knew that these are the directions, the kind of the principal axes of growth in this system, the Z1 and Z2 directions. And just with that information, I could draw this phase portrait. Good. We call this an unstable source or a node. This is called an unstable source. It's literally like a source. Okay. Sometimes this is called a node in dynamical systems. This is as opposed to something called a sink. If I reversed all of these directions and I made these negative eigenvalues, all of these arrows would be pointing in, and I would have stable dynamics, e to the minus 2t, e to the minus 4t, where everything comes in. That would be a stable sink or a stable node. Okay, so maybe I'll just take 2 minutes and I'll show you kind of what that would look like. Where am I going to do this? Maybe, okay, I'm going to erase this, and then I'll tell you what would happen if this was stable. Just stay put. Okay, so for this dynamical system with these two unstable eigenvalues, meaning that they have a positive real part, so they grow exponentially positive exponential in time, I have this unstable source behavior. Things blow out from the origin exponentially fast. If I just change the direction of time here, this is actually kind of a good exercise. If I literally just said, you know, x dot equals minus this ax, that's just going to change the direction of time. It's almost like saying time reverses, and instead of everything fleeing from this origin, everything's going to attract to the origin. I just want to show you really quickly what changes up here, what changes here, and how this diagram changes. Okay, so if x dot equals minus ax, so this equals, you know, minus 3 plus 1 plus 1 minus 3. I'm pretty sure, and this is something you should check in by hand, in Python or in MATLAB, is that I'm pretty sure that t and t inverse don't change, and only d changes. So I think what that means is that d now is going to have negative eigenvalues, negative 2, 0, 0, minus 4. And the only thing that's going to change here is that this is going to become z dot equals minus 2 z1, z2 dot equals minus 4 z2. And now these are negative exponentials, meaning as time goes to infinity, these actually approach 0. And all that's going to happen in this diagram is all of the arrows are going to reverse. So all of my arrows going out are now going to point in. And this would be called a stable. Instead of a source, it's a sink. Just like you turn on your faucet and water flows into the sink and it all drains, that's kind of like what this is going to be. It's called a stable sink. And I think that's also called a stable node in dynamical systems. And I can probably draw this picture pretty quickly. I'll just draw the real quick and dirty sketch of this thing. It's basically going to, you know, have exactly the same pattern of approach. But now all of these arrows are going to be, I'm doing kind of a bad job, but now all of these arrows are going to be pointing in towards the origin. And still in the C2 direction, they're going to be pointing in faster than the C1 direction, but everything is eventually going to be pulled in to the origin. This really shouldn't be pointed like this. They should all be pointed into the origin. I did kind of a bad job over here. They're all going into the origin. Okay, this is called a vector field, if you like, because it's literally a field of vectors. At every point, there's a vector pointing in a direction. And that vector field is literally the x1 dot and x2 dot components. The components of this derivative form a field of vectors pointing in. This is a stable sink. Okay, so this is one cool example with real eigenvalues, distinct real eigenvalues. In the next few lectures, we're going to look at cases where what if one of these is positive and one of these is negative? That's called a saddle point. What if we have a case where these are complex conjugate pairs, maybe a plus I and a minus I? I'll show you that in that case you get sines and cosines, kind of oscillatory dynamics, rotating dynamics in this phase plane. And then we'll start looking at how you can analyze nonlinear systems with these linearizations close to these fixed points. That's all coming up. Thank you.